So if you traveled back to, say, 1861,
Okay.
and you looked at this young boy who had calves the size of professional athletes,
Yeah.
you would probably think he was just the absolute picture of health. Like, you'd see these massive bulging muscles and just assume, wow, he is incredibly strong.
Obviously.
But what you wouldn't realize, and this is wild, is that those muscles were actually destroying themselves from the inside out. Like, the map of his body was just completely lying to you.
It really was. The visual evidence totally pointed to strength and growth, right? But the actual biological reality underneath was just catastrophic weakness.
Yeah.
And it's really a perfect example of how the labels, the words we use to describe the body, they can sometimes completely mask what is actually happening under the surface.
Exactly.
Yeah.
So today on the deep dive, we are decoding how we talk about what our bodies are doing. We're specifically looking at the vocabulary of movement, of paralysis, and of growth.
Oh, it's a great topic.
Yeah. We're going to examine a family of 3 incredibly powerful medical word-building blocks. So that's kinesio, plegia, and atrophy.
And these are terms that all cluster around basically the body's physical capabilities, like what the muscles and nerves are doing or failing to do.
Right.
And they carry this massive hidden history because, well, they originate from ancient Greek. But as we peel back the layers on these words today, we're going to see how modern science has been forced to just completely flip our understanding of them.
It's quite a ride.
It is. I mean, we're dealing with everything from locked-in consciousness to, the physiological changes that astronauts undergo in space, and of course the really tragic reality of those young boys in 1861 that you mentioned.
Okay, let's unpack this. We have to start with the baseline of how our bodies interact with the world around us, which is, motion, the engine of movement itself.
Foundation.
Exactly. Right. And this brings us to that first root word, kinesio, which it comes from the Greek kinesis, meaning movement or motion. We usually hear it in a word like kinesiology, right? The study of how the body moves. But it gets incredibly specific when we start attaching prefixes to describe the actual quality of that movement.
It does, yeah. And to understand how those prefixes modify kinesis, we have to look at the actual mechanism of movement.
Like what's happening in the brain.
Right, because the brain doesn't just, push a single button to make your arm move. It is this highly complex negotiation between different regions. So the motor cortex drafts the plan.
Cool.
But there's this structure deep in the brain called the basal ganglia, and it acts sort of like a committee.
Like a committee?
Yeah, a committee that has to approve and smooth out that movement plan before it ever sends the signal down the spinal cord.
So, okay, think of kinesio kind of like a tempo dial on a music player.
Oh, I like that.
Yeah, so like if we take a word like bradykinesia, brady means slow. So on our music player, the tempo dial is just dragging.
Dragging, right. And if we apply that to the brain's committee, in a condition like Parkinson's disease, the neurons producing dopamine start to die off.
And dopamine is
It's essentially the chemical currency that the basal ganglia committee uses to communicate. So when dopamine drops, the committee just stalls out.
Wow, okay.
The brain is still trying to send the signal, but the approval process is dragging. So you get this abnormally slow, really hesitant execution of movement. The tempo dial is stuck on slow.
That makes so much sense. And then if we flip it, look at the other extreme, hyperkinesia, where hyperkivi is, excessive.
Right.
Now the tempo dial is on fast forward. The committee just completely loses its brakes.
Exactly. It loses inhibitory control. So the movement commands are just firing off rapidly, which looks like restless or jerking, writhing motions.
And then I guess if you hit pause completely, you get a kinesia, a meaning without. Just total absence of movement.
Exactly. The signal is entirely blocked. But, what's fascinating here is how kinesio connects to a whole constellation of neighboring terms. It's not just the motor output.
Right. There's a whole ecosystem of words.
Yeah, like how we weave in prefixes like myo, which means muscle, or neuro, meaning nerve. But even more interesting is the sensory side. Take the word kinesthesia.
Kinesthesia, okay.
We're combining movement with esthesia, which means sensation.
Oh, like anesthesia.
Exactly, without sensation. But kinesthesia is your nervous system's internal monitoring system. You have these specialized receptors, proprioceptors in your muscles and joints, and they are constantly pinging the brain with real-time data about exactly where your limbs are in space.
Oh, so that's why you can touch your nose with your eyes closed.
Yes, exactly.
Like your brain doesn't actually need to see your arm to know it's moving because it's feeling the movement internally.
Right. The system is reporting back on itself, and that feedback is so crucial because, you can have perfect kinesis, the muscle contracts beautifully, but you could still suffer from ataxia.
Ataxia. A meaning without and ataxia meaning.
Order or coordination.
Okay.
So if the cerebellum, the part of the brain that calibrates all this timing, gets damaged, the movement happens, but it's totally chaotic, it's clumsy.
Like the tempo dial is working.
Yeah.
The music is just a jumbled mess.
Exactly. Completely uncoordinated.
Okay, so building directly on that tempo dial analogy, what happens when the connection to the dial is just severed entirely? We're talking about transitioning from movement to actual paralysis.
Right, the engine stops.
Exactly.
Huh.
And that brings us to our second big medical building block, which is atrophy.
Yeah, so plegia originates from the Greek word plege, which actually meant a stroke or a blow, like a physical blow.
Wow.
But it evolved in medicine to mean paralysis, and we usually see it attached to body regions to describe, where the connection got severed.
Right, like hemiplegia is one side of the body.
Yep. Paraplegia is the lower body. Quadriplegia, or sometimes called tetraplegia, is all 4 limbs.
Monoplegia for one limb, diplegia for symmetrical parts, usually both legs.
You got it.
But wait, let me push back on this for a second, because in everyday conversation, isn't paralysis just a simple, absolute on-off switch?
What do you mean?
Like, you either can move or you can't. The wire is cut. Isn't that what plegia means? Just a total 100% shutdown.
That is definitely the everyday assumption. But the clinical reality is way more nuanced. Modern neurology draws a very hard line here. Plegia signifies a complete loss of voluntary motor function, the total shutdown.
Okay.
But we also have paresis, which means partial weakness.
Oh, so hemiplegia means the whole left side is completely offline. But hemiparesis means it's just very weak. The wire is damaged, but not fully cut.
Exactly. It's a brownout, not a blackout. And it completely changes how a doctor approaches the patient. Plus, even with true plegia, paralysis isn't just one thing. It's split by mechanism. We have to talk about flaccid versus spastic paralysis.
Okay, flaccid is what I think of normally.
Yes.
The muscle is just totally limp.
Right.
The signal never reaches the muscle, so it just hangs there completely inert.
Yes. But spastic paralysis visually looks like the exact opposite, even though the person still has 0 voluntary control.
Wait, how can paralysis look like the opposite of limp?
Because the spinal cord has its own built-in reflex loops, like when the doctor taps your knee with that little hammer and your leg kicks.
Oh, right, the knee-jerk reflex.
Yeah, your brain doesn't do that. The spinal cord does it automatically. Normally, your brain is always sending signals down to essentially tell the spinal cord, hey, relax, don't overreact to every little stretch.
Oh, so if you have an injury high up in the brain or the upper spinal cord.
You lose the ability to move, but you also lose the relax signal.
Wow.
So those spinal reflexes are left completely unchecked. The muscles get incredibly stiff, rigid, they spasm violently, the paralysis is rigid.
That's terrifying, actually.
It is. Dr. William John Little, back in 1861 and 62, he made some of the first major clinical observations of this.
Right.
He was watching children who had profound difficulty walking, and their legs were super stiff, almost crossing like scissors when they tried to move.
Scissors.
Yeah, scissoring gait. He was witnessing spastic diplegia. The neurological damage, which was usually from a lack of oxygen during birth, left those lower limb reflexes totally unchecked.
So it's not an absence of action, it's this agonizing excess of involuntary action.
Exactly, which laid the foundation for what we now call cerebral palsy.
And this total disconnect between the brain and the body, it really makes you think about profound historical examples, like the famous case of Christopher Reeve.
Oh, absolutely.
He suffered an injury incredibly high up on his spinal cord, which caused profound quadriplegia. The main cable was cut, essentially.
Yeah, severing that connection completely. But for me, the most profound illustration of how specific paraplegia is to just the motor pathways is locked-in consciousness.
Oh, man. Yeah, the Jean-Dominique Bauby case.
Yes, it's just staggering. So in 1995, Bauby, who was the editor of the French magazine Elle, he suffered this massive stroke right in his brainstem.
And the brainstem is basically the funnel where all the motor wires bundle together before they go down the spine.
Right, and the stroke destroyed that funnel. So he wakes up and he has total plegia of almost his entire body. He can't move, he can't speak, he can't swallow, or even breathe on his own.
And this is the terrifying part. The pathways for consciousness and memory and intellect, they don't route through that exact same spot.
Exactly. They were spared. So he was fully awake, fully aware. He had this hyperkinetic mind, a brilliant mind, just trapped inside a completely akinetic body.
The only thing he could move, the only wire that survived, was his left eyelid.
Yeah.
And he used that one eye to blink. He blinked to select letters as an assistant, read the alphabet out loud, and he wrote an entire book, The Diving Bell and the Butterfly, literally one blink at a time.
It is just an unbelievable testament to human endurance. But medically, it really proves that plegia paralysis does not mean a loss of the self.
No.
The central command was fine. It was just completely disconnected from the rest of the body.
So, okay, if the plegia is the electrical wiring failing, what happens to the hardware itself?
Yeah.
To the muscle tissue over time when it's disconnected? That transitions us right into our third medical block.
Atrophy?
Trophy, yes.
So polyphy and the adjective form atrophic, they come from the Greek word trophy, which literally meant nourishment or food.
Food.
Yeah, food. And historically, it became the suffix we use to describe the size or growth or the wasting away of tissues, especially skeletal muscle.
Right, so let's run through the core definitions. You've got atrophy, A meaning without.
Yeah.
So literally without nourishment, which is muscle wasting.
Correct.
Hypertrophy.
Hypertrophy.
Excessive nourishment, that's when a muscle gets huge like a bodybuilder.
Yeah.
And dystrophy, meaning bad or defective, pointing to like abnormal, usually genetic developmental issues.
And those textbook definitions, they serve medicine perfectly well for hundreds of years.
But here's where it gets really interesting, because in the 20th century, with molecular biology exploding, that entire conceptual framework completely fell apart.
Totally. Because again, the Greeks literally meant food. They thought if a muscle was shrinking, it was starving.
Which seems super logical.
Right. Before you can look inside a cell, it makes perfect sense. But modern science proved you can have severe atrophy or a terrible muscular dystrophy in a person who is eating massive amounts of protein and calories.
So the ancient words stayed, but the underlying mechanisms they were describing totally changed.
Completely. We realized that muscle tissue is actually just very metabolically expensive for the body to keep around.
Take a lot of energy.
A lot. So to justify keeping it, your body requires two things: constant nerve signaling and immense mechanical stress.
Physical load.
Exactly. It's not about the food, it's about the load.
Which brings us to the craziest paradox.
Yeah.
Spaceflight atrophy.
Oh, yeah.
You've got astronauts, right? They are literally the peak of human fitness. Highly active. Eating these scientifically perfect, hyper-nourishing diets.
Tons of trophy.
Tons of it. And yet they go into space and they lose muscle mass at an incredibly alarming rate.
Because they lose gravity. Gravity is the constant mechanical resistance our bodies evolved to fight. You take that away in microgravity and the body says, hey, keeping these massive leg muscles is a huge waste of energy now.
Wow.
So it actually activates these cellular pathways. There's one called the ubiquitin proteasome system, which literally tag the muscle proteins for destruction and just shreds them down.
The body just cannibalizes its own hardware to save energy.
Exactly. So the Greek idea of just lacking nourishment is totally inadequate to explain aerospace medicine.
So wild. But if we connect this to the bigger picture, it gets even stranger on the other end of the spectrum. Like what happens when a muscle looks like it's growing massive hypertrophy, but it's actually failing?
Pseudohypertrophy.
Which takes us right back to 1861, to the French neurologist Guillaume Duchenne and those young boys I talked about in the very beginning.
Yeah, Duchenne documented these boys who had profoundly enlarged calves. I mean, visually, it looked like they were doing intense strength training, huge hypertrophy.
But they were tragically weak. They could barely stand up.
Right, and you ask, well, how does a muscle get that big if it's weak? Because it's not true hypertrophy. It's what we now call Duchenne muscular dystrophy.
Okay.
And that visual enlargement is pseudohypertrophy. Pseudo meaning false. We now know it's a genetic mutation in a protein called dystrophin.
Dystrophin.
Yeah, it acts like a shock absorber for the muscle cell. Without it, just the normal, everyday stress of walking literally tears the muscle fibers wide open.
So just by walking, they're constantly sustaining microtraumas.
Exactly. The muscle fibers die off, so they atrophy, but the body tries to heal the void by rushing in inflammatory cells, fat, and scar tissue.
Oh, wow.
So the volume of the calf expands with all this non-functional junk tissue, making it look big and healthy, while the actual engine is just being systematically destroyed.
And MAP says hypertrophy, but the territory is just total devastation.
It's a really sobering reminder that volume doesn't equal health.
And staying with that 19th century French neurology era for a second, Jean-Martin Charcot, who actually taught Duchenne, he uncovered another massive twist here. With a condition called Charcot-Marie tooth disease, or CMT.
CMT is such a brilliant example of how the electrical wiring and the hardware are interconnected, because a patient with CMT will show up with really severe muscle atrophy, mostly in their lower legs and hands.
So the muscle is wasting away.
Wasting away. And if you just look at the muscle, you'd think it's a disease of the muscle itself.
It's actually a disease of the nerve.
Exactly. It's a genetic neuropathy. The mutation degrades the myelin sheath, which is the insulation wrapped around the nerve fibers.
Okay.
So without insulation, the electrical signal from the brain just leaks out. It degrades before it ever reaches the muscle. And because the muscle isn't getting those electrical pings saying contract, it just rapidly atrophies from disuse.
So the muscle itself is genetically totally fine. It's just starving for electrical stimulation.
Exactly. The wiring fails, so the architecture collapses.
Unbelievable. Now, before we completely leave the concept of growth, we should probably touch on this really interesting ongoing debate in sports science about how muscles actually get bigger.
Right, hypertrophy versus hyperplasia.
Because we know that when a bodybuilder lifts weights, they undergo true hypertrophy. Like, the existing muscle cells they already have just balloon in size. But then there's this other word, hyperplasia.
Yeah, so hyperplasia refers to an actual increase in the number of cells, not just the size.
Okay.
So if hypertrophy is like blowing more air into a balloon.
Hyperplasia is like just buying a second balloon.
Exactly. And we see hyperplasia happen in other tissues in the body, right?
Yeah.
Like skin regenerating or the lining of the uterus thickening.
But the big question is, does it happen in human skeletal muscle?
Mm.
Can you actually grow brand new muscle fibers from scratch just by lifting weights?
And that is the massive debate. We know it happens in animal studies, like extreme mechanical overload in birds and cats can force these muscle stem cells to form brand new fibers.
Wow.
But proving it in living humans, practically impossible. You'd literally have to surgically remove a muscle, count tens of thousands of microscopic fibers, put it back, have the person work out for 5 years, and then remove it to count them again.
Yeah, nobody's volunteering for that study.
No, exactly. So the scientific jury is still totally out. We know human muscles get thicker, but whether we're just blowing up the balloons we have or slowly adding new ones, it's a mystery. So for now, doctors stick to using hypertrophy.
Right. Okay, so what does this all mean? Let's take a step back and look at the territory we've covered today on this deep dive.
It's a lot.
It is. We started with kinesio, this ancient Greek concept of motion.
Yeah.
Saw how complex it gets when dopamine drops or the cerebellum loses its rhythm.
Right.
Then we explored plegia, moving way past the idea of a simple off switch to uncover, partial weakness, spastic reflexes, and the haunting reality of locked-in syndrome.
Yeah.
And we finished up with atrophy, tracking how molecular biology kind of hijacked a word meant for nourishment to explain microgravity, genetic mutations, and nerve insulation.
And I think the overarching theme of this entire discussion is really adaptation. But not just biological adaptation, linguistic adaptation.
What do you mean?
Well, the reality is that scientific discovery always outpaces the language we have to describe it. We are effectively diagnosing 21st century genetic and neurological conditions using the vocabulary of a 4th century BCE philosopher.
Wow. Yeah.
We are forcing these incredibly complex, brand new biological realities into old, rigid linguistic boxes.
And I think understanding that disconnect is what makes you, the listener, a much more informed, critical consumer of medical information. Like when you hear a doctor use a label like paralysis or atrophy, you now know that label isn't the final answer.
Exactly. It's just the opening line of a much deeper clinical conversation.
To look past the map and ask about the territory, like, is the weakness flaccid or spastic?
Right. Or is the atrophy coming from a diseased muscle or a demyelinated nerve? Are we looking at true muscle growth or just the tragic illusion of pseudohypertrophy?
It fundamentally changes the resolution at which you view the human body.
It really does. And, this raises an important question, something for you to mull over long after this deep dive ends.
Okay, let's hear it.
We can look back at the last century and see so clearly how molecular biology forced us to redefine what ancient words like trophy mean. We had to completely abandon the literal translation of nourishment because it just wasn't true anymore.
Right, because the original architects of those words, they didn't know about DNA or ubiquitin pathways or dopamine.
Precisely. So the question is, What current, everyday medical terms are we using right now with complete and utter confidence that the next century of scientific breakthroughs will prove are based on entirely outdated assumptions?
Oh, man.
What is our modern-day equivalent of believing that muscle shrinkage is just a lack of food?
We might literally be looking at our current medical dictionaries 100 years from now, the same way we look at a flat Earth map. The blue lines are drawn, the labels are printed, but the territory is about to change entirely. Keep questioning the map, everyone. We'll see you next time.